I am Professor Professor Gaikwad from Bangalore Science College, Bangalore. Now we are learning a topic sequences. Okay. Now we will quickly revise. So what we have learned in previous lectures. Okay. Now we have seen sequences, and we know that sequence may be bounded or unbounded. Okay. Now we also see the definition of convergent sequence. What is convergent sequence? Sequence which have a proper limit. Okay. Or if limit of sequence exists, then sequence is said to be convergent sequence. And we have seen one important criteria for sequence to be convergent, and that is that sequence must be bounded for it to be convergent. Okay. So if sequence is convergent, it must be bounded. Okay. Now, so we'll quickly revise this basic concept. Okay. Now, sequences can be of two types, either bounded sequence or unbounded sequence. Now, we have seen for sequence to be convergent, sequence must be bounded. So only bounded sequence can be convergent. If sequence is unbounded, it must be divergent. Okay. Now, we will first go to the type of bounded sequences. Okay. A bounded sequence which has some upper limit and lower limit, or upper bound and lower bound. Okay. So now bounded sequence either convergent or divergent, but divergent of the type they are oscillates finitely. Okay. We have seen example. See the example, the sequence 1 by n. Okay. This is the we have seen bounded sequence, and it is convergent, and its limit of the sequence is 0. Okay. Now we will see, we have seen another example. Example is sequence -1 raised to power n. Okay. This sequence has the element plus or minus 1. Okay. This sequence is also bounded, has upper bound 1, lower bound -1. Sequence is bounded but not convergent. Why? Because if we take two different subsequence of the sequence, we get two different limit. And we know if sequence is convergent, it must has a unique limit. Okay. Now limit of this sequence is 1. Okay. When n is even and -1 if n is odd. So this sequence has two different limits depend on value of n. So this sequence is not convergent. But since it has two different limits, 1 and -1, we say this sequence is oscillate, and limits are finite. So we say this divergent sequence is oscillate finitely. So this is the one type of divergent sequence. Okay. Sequence is oscillating finitely. Okay. Sequence oscillate between two limits, 1 -1, 1 -1. So this sequence is oscillatory sequence, and it oscillates finitely. Okay. Because it has two finite limits. Now we know a type of unbounded sequence. Now for sequence to be convergent, sequence must be bounded. So unbounded sequences are all divergent sequence. Again there are two types. Either they are directly divergent to plus or minus infinity. We have example sequence here. Okay, the term is 1, 2, 3. These are the up to so on. These are the elements of this sequence. Now this sequence is unbounded, and if we try to take the limit of this n term as n tend to infinity, n term also tend into plus infinity. So this sequence is divergent to infinity. Okay. So this is one type of divergent sequence, which are tending to infinity. Now second type of unbounded sequence is which is also divergent sequence, but they oscillate infinitely. Here sequence is oscillating finitely. Say example, you take -1 raised to power n into n. Okay. Now if we take n even number, limit of sequence becomes, so -1 raised to power any even number become +1. So sequence become like this n. This sequence as n tend to infinity goes to infinity. Okay. Now if we take n as an odd number, Then minus 1 is to any odd number is minus 1. So sequence become sequence of minus, okay, yeah, minus 1, minus 2 up to so on. So this sequence diverges to minus infinity. So if we take any odd, sequence diverges to minus infinity. So this sequence has two different limits. Sequence diverges to two different points. One is plus infinity, other is minus infinity. We say this sequence is oscillate, but oscillate infinitely because limit does not exist. It tends to infinity. Here limit exists and it is finite. But the only problem was there are two limits. Here sequence diverges to plus infinity or minus infinity, depend on the value of n. So we say that this sequence is also divergent, but we can say that this sequence is oscillate infinite. Okay, these are also some type of sequences. I hope you understand this. Okay. Now there is very simple theorem on the sequences. Okay, so we will see this theorem now. Theorem is we have given two sequences. One is x is equal to sequence defined by n term xn, another is sequence y defined by n term yn. Okay, these are the two sequences in real numbers. Okay, and this sequence xn given by capital X converges to say small letter x, and this sequence y converges to small letter y. Okay, now we have to prove that there is a sequence x plus y formed by addition of these two sequences converges to addition of their limit, that is sequence x plus y converges to their limits, sum of limits small x plus small y. X minus y converges to x minus y, x into y converges to product of limit, and if c is any real number then c into x converges to the c into limit of sequence x. That is, you have to show if there are two convergent sequence, then sum of two sequences converges to sum of their limits, subtraction of two sequences converges to subtraction of their limits, product of two sequences converges to product of their limits, and if you multiply some sequence by some constant number, then that sequence converges to product of that constant number and limit of the original sequence. Okay, so this is a very simple theorem. Okay, so now we will first prove that the sequence addition of sequence converges to the addition of their limits. Okay, so we have already given sequence xn converges to x and this sequence converges to y. By definition, for any epsilon greater than 0, okay, now so we will first write given part. Okay, now we have given that sequence xn converges to x and sequence yn converges to y. Okay, so by definition of limit of sequence for any epsilon greater than 0, there is a natural number m1 and also natural number m2, m1 for this sequence, m2 for this sequence, such that whenever n greater equal m1 implies the distance between elements of the sequence and limit of the sequence is less than some very small number, arbitrary number, that is epsilon by 2. We can take it epsilon by 3. Okay, for adjustment we have taken epsilon by 2. This is the definition of limit of sequence. Also, since y converges to y, there is another natural number m2, such that whenever n greater equal m2, we have distance between the sequence yn and its limit less than epsilon by 2. Okay, so we have get here two questions. Okay, now see, this distance is less than epsilon by 2 whenever n greater equal m1, and this distance also less than epsilon by 2 but when n greater equal m2. If we take new value of m, okay, if we take m is equal to maximum of m1 and m2, that is, we have taken a number which is greater than m1 also greater than m2, then for this m both this inequality will be valid, because when n greater equal m1, this is valid, but m1, this m is maximum of m1 and m2, so m may be greater than m1. So whenever n greater equal m1, this is true. So n greater equal, whenever n is greater equal capital M, this must be true, because m is greater equal m1, and this is true for any value greater equal m1. Similarly, m is maximum of m1 and m2, so m is greater equal m2 also, and this is true for any value which is greater equal m2, and m is greater equal m2. So whenever n greater equal m, this is also true. So if we take m is equal to maximum of m1 and m2, both inequality valid at the same time. So whenever n greater equal m, this is also less than or number 2, this is also less than or number 2. Okay, we get mod of xn minus x less than epsilon number 2 and mod of yn minus y less than epsilon number 2. Okay, so this is true for n greater equal m. Now we have to prove that the sum of these two sequences xn plus yn converges to x plus y. So we will take mod of sum of two sequence xn plus y minus, we have to prove sequence xn plus yn converges to their sum of their limits. So we have to prove the difference between the sequence and limit is less than epsilon. Okay, so we have taken this mod. We can write this as, this is equal to, just take x and x in one bracket and y and this y in one bracket. So we can write this as x and this minus of x, so that it is plus y and this and minus of y. Okay, so next there is some small arrangement. Okay, adjustment. Now we know triangle of mod of a plus b always less equal mod a plus mod b. So by triangle law we can write this as mod of xn minus x plus mod of yn minus y. Okay, what is triangle law? It is mod of a plus b always less equal mod a plus mod b. Now for n greater equal m, this value is less than epsilon by 2. Also, this value is less than epsilon by 2. Okay, so from this we can write this is strictly less than, this is less than epsilon by 2, this is less than epsilon by 2. So sum is epsilon by 2 plus epsilon by 2 is epsilon. Okay, so we have shown whenever n greater equal m, for any epsilon greater than 0, for any epsilon greater than 0, and whenever n greater equal m, difference between xn plus yn and x plus y is less than epsilon. So by definition of limit, this sequence converges to this limit. So we can write the sequence xn plus yn converges to x plus y. That is, we can write this as capital X plus capital Y. Okay, so we have proved that sum of two sequences converges to sum of their limits. Okay, so similarly it will be very easy to prove that difference between two sequences is converged to difference between their limit. Just instead of plus use minus and make some arrangement. Okay, so I left this part to you. Now we will prove that the product of sequence converges to product of their limits. Okay, now we will go to the next part of theorem. So in next part we will prove the product of two convergent sequence is converges to product of their limit. Okay, so we have given two sequence, x is equal to xn converges to x and y is equal to y converges to y. We will prove this product of these two sequence x into y converges to x small x into small y. That is, product of sequence of limit converges to product of their limits. Okay, so we have to prove here that sequence xn yn converges to x into y. Okay, we have to prove this. Where xn converges to x, yn converges to y, then xn into yn converges to x into y. We will do this. Okay. Now again we will use definition of epsilon and epsilon delta definition of limits of sequence. Okay. So we will take difference between sequence and this value x into y. So xn into yn minus x into y. So we will make here some adjustment. So xn into y. Now we will subtract and add one term. The term is xn into y. Okay. As we have subtracted this term, we have to add this term so that both sides will be same. Okay. Since we have added this, we have subtracted this term, we have to add this term. So we have to add this term. So xn into y. Okay. And last term as this minus x into y. Okay. Minus x into y. What we have done, we have just added x into y and subtract x into y. So these two values, both sides are same. Okay. Now this is equal to, from first term we can take xn common. So mod of xn and this is yn here minus y. Okay. Plus from last two terms y is common. So take y outside and write remaining term xn minus x. Okay. Again mod of a plus b. So again we will use triangle law. This is less equal mod of a plus mod of b. So mod of xn into yn minus y plus mod of y into xn minus x. Okay. This is less equal mod a plus mod b. So again this is less equal. These are the two terms imported. So we can take mod of xn into mod of yn minus y. Okay. We have just taken xn outside, but it is in mod. So mod of xn. Similarly, we take y outside, but it is in mod. So we can write mod of y into mod of xn minus x. Okay. Now sequence xn is convergent, so it must be bounded. Okay. Also y is nothing but the limit of the sequence yn, so it is also some element of real numbers. So both these elements are bounded. Okay. Now we will take a number which is maximum of y and mod of xn. Okay. So we write here a is equal to maximum of mod of xn and this number mod of y. Okay. As sequence xn is bounded, the n term mod of xn is some real number bounded. This mod y is limit. It is also some real number. So we take maximum of these two numbers. Okay. As this NHS is less equal this value, and we are just taking a instead of mod of xn and mod of y. This value a is greater equal this value, also greater equal this value. So this total term also less equal to the. So we are LHS as it is. So mod of xn yn minus x into y less equal. This was less equal this, and we are again writing a term which is also greater equal this, because we are taking maximum of mod of xn and mod of y. Okay. This term already was less equal this, and we are writing again a term which is greater than this. Why? Because we are replacing mod y and mod xn by a number which is greater equal to them. Okay. It's greater than or equal to these two terms. Okay. So again this side is less equal. Okay. This is again less equal. Replace this term by a. So a into mod of yn minus y. Replace this mod y by a. because we are taking a number greater equal these two terms, which is a. So again, plus a mod of xn minus x. Okay. Now we know this sequence xn converges to x and yn converges to y. So by definition of limit, for any epsilon greater than 0, there exist two natural numbers, m1 for first sequence and m2 for second sequence, such that whenever n greater equal m1, we have distance between sequence and its limit xn, the sequence limit is x is less than some very small number, any arbitrary number, and we take this number as epsilon upon 2a. Okay, we have taken this number. Now we know a is a positive number because this maximum of mod of x and mod of y. So by definition, distance between these two elements is less than some positive number. Also, whenever n greater equal m2, we know distance between the sequence yn and y, limit of yn is y, also is there some positive number which is less than epsilon by again twice a. So we know if we choose m is equal to maximum of m1 and m2, then these two inequality, okay, these two equations satisfied for single value of m. Okay, as we taking m, see, whenever m greater equal m1, this is less than epsilon by twice a, and already m is greater equal m1, so whenever m greater equal m, this is less than epsilon by twice a. Similarly, whenever m greater equal m2, this is true, and m is greater equal m2, so whenever m greater equal m, this is also true. So for m is equal to maximum of m1 and m2, both these conditions are true. So we write mod of xn minus x is less than epsilon by twice a, and mod of yn minus y also less than epsilon by twice a for n greater equal m. Okay, put these two values in our this equation. Okay, so we have to put this value in this equation. So we get mod of x and y minus xy, which is less equal a into mod of yn minus y, but mod of yn minus y is less than epsilon by 2a. So we write this is less than epsilon by twice a plus a into mod of xn minus x, but mod of xn minus x is less than epsilon by twice a, and this is happening for epsilon greater than 0 and n greater equal m. So for epsilon greater equal 0 and n greater equal m, this is happening for whenever n greater equal m. Okay, now this a get cancelled, so it is less than epsilon by 2 plus epsilon by 2, that is less than epsilon. So for any epsilon greater than equal to 0, there exists a m such that whenever n greater equal m, distance between x and y and xy, or mod of x and y minus xy is less than epsilon. So by definition of limit, this sequence x and y converges to the x into y. So by definition of limit of sequence, this sequence x and y is converges to the limit x into y. So product of sequences converges to product of limit. Okay. Also, there is one more part of this theorem which is also very simple, and we can prove that as sum of two sequences converges to sum of their limit, difference of two sequences converges to difference of their limit, product of two sequence converges to product of their limits. The division of two sequence converges to division of their limit, but only condition is here is that this y, which is limit of sequence y, must not be 0. Okay, if this becomes 0, something upon 0 which is not defined, so y must be not equal to 0. So this is very easy theorem. Okay, now we will see some example on these theorems. Before going to the examples based on previous theorem, we will see one more important theorem. Now this theorem is limit of x to the power n is equal to 0 as n tends to infinity when mod of x is less than 1. Okay, so this is the sequence whose n term is x to the power n. Then limit of this sequence is 0 whenever the value of x lies between minus and plus 4. Okay, this is very important theorem, that limit of this x to the power n whenever mod of x is less than 1 as n tends to infinity is equal to 0. Okay, now if x is greater than 1, then limit obviously will be infinity. So limit is equal to 0 of x to the power n as n tends to infinity whenever the value of x lies between minus and plus 1, that is mod of x less than 1. Okay, now this is a very important theorem. Now since mod of x is less than 1, that is we can write as minus 1 is less than x less than 1. This means this. So either we have two options. Since 0 lies between minus 1 and plus 1, either x is equal to 0 or x not equal to 0. Okay, since value of x lies between 1 and minus 1. If x is equal to 0, this becomes 0 and limit of g constant 0 is 0. So there is nothing to prove if x is equal to 0. So for x is equal to 0, theorem is trivial. So we will focus on the value of x which is not equal to 0 and lies between minus 1 and plus 1. Okay. Now we have to prove limit of this sequence is 0. So for that purpose, we have to prove that for any epsilon greater than 0, we have to find an actual number m. Okay, such that whenever n greater than equal m, we must have distance between or mod of the sequence and limit is less than epsilon. So if we find value of m satisfying this condition, we will prove limit of this is 0. Okay, so for that purpose we have to find the value of m. Okay, so let us assume this is true, that is this mod is less than epsilon. Okay, so x is to n minus 0 means x is to power n, so this applies. So let is less than epsilon, that is mod of x is to power n is less than epsilon. Okay, because x is to n minus 0 is x is to power n, which applies mod of x to power n is less than epsilon. Okay, this is true if only this is true, this is true if only this is true. Okay, now we will take log on both sides. Okay, because we have to find value of n which is greater or equal to m, so we have to find the m and n such that whenever we have to find m such that whenever n greater or equal to m, this condition is satisfied. Okay, so we will take log on both sides. So this is true if and only take log to the base 10 on both sides. Log to the base 10 of mod of x is to power n is less than log to the base 10 of epsilon. But the problem is here. Okay, here mod of x is less than 1. So we will come to this point. So this happens if only n log to the base 10 of mod x is less than log to the base 10 of epsilon. Now here value of mod x is less than 1, and we know one property of log of a is negative when a is less than 1. So log of negative number, so log of a number, so not negative number, log of a number which is less than 1 is always negative, less than 0. Here mod x, see value of mod x is less than 1. If a is less than 1, log of the value is less than 0. So this is negative. So here we have to change the sign. Since this number is negative, and this previously this was less than this. So if there is, now we are taking negative sign. So this inequality, that is less than, must be changed to greater than. See, we know 1 is less than 2. Okay, 1 is less than 2. But if we give minus sign to the 2, then this becomes 1 is greater than minus 2. Okay, so this and so we know the basic thing. So since this is negative, we have to change the this inequality. So this less than become greater than. Okay, so we can write here that this happen if and only if n log to the base 10, here log to the base 10 of mod x is greater than log to the base 10 of epsilon. Why we are changing this inequality? Because the log of this number is negative. Since log of this number is less than 0. So from this we get the value here. Just transfer this value to this side. So if I leave n is greater than this log to the base 10 of epsilon upon log of mod x. Okay. So whenever n greater than this happen, and this happen. So whenever n, so we have to choose this value as a m, because whenever n greater than n greater equal m, difference is going to be less than epsilon. See, whenever n greater than this, we get difference between x to the power n and 0 is less than epsilon. So we have find the value of m. So choose m, a number greater equal this. So choose number m greater equal this log of epsilon upon log of mod x. So using this value, so whenever if we choose this value, choose value of m greater equal this, and whenever n greater equal this m, whenever n greater equal this m, we get the difference between x to the power n and limit less than epsilon. So whenever n greater equal m, we get difference between our sequence x to the power n and the element 0 less than epsilon. This means limit of this sequence is 0. That is, limit of x to the power n is equal to 0 as n tends to infinity whenever mod of x is less than 1. This is also one important theorem of limit of sequence. Okay, using previous theorem, we will solve some examples to find limit of the sequence whose n terms are given. Okay, so here we are saying is twice n square minus n upon n plus 7, and we have to find the limit of this n term. Okay, so first of all, we will divide numerator and denominator by n. Okay, so dividing numerator and denominator by n, we get Sn is equal to, okay, so limit of Sn is equal to limit of, so just divide numerator and denominator by n. Okay, so this become twice n square upon n and minus n by n. Okay, so twice, or we write one more step, twice n square minus n upon n upon n plus 7 upon n. Okay. So separate these things. So twice n square upon n minus n by n. This becomes limit of. So twice n square upon n means twice n minus limit of n. Okay. Limit of n by n, which is 1 upon n by n is 1 plus 7 by n. Okay. Now we know limit of xn upon y is equal to limit of xn upon limit of y. So we will separate the limits. This becomes limit of numerator and limit of denominator. So limit of, and we can also know limit of xn minus y and limit of xn minus limit of y. So separate. So limit of this becomes limit of twice n minus 1 upon limit of 1 plus 7 by n. We have used limit of xn upon y n is equal to limit of xn upon limit of y. Now use limit of xn minus yn, which is equal to limit of xn minus limit of yn. So this becomes, we take to outside, so 2 into limit of n as n to infinity minus limit of constant 1 is 1, so limit of 1 upon again limit of 1 plus 7, we can take outside, 7 into limit of 1 by n. So as n tends to infinity, limit of n is infinity, so 2 into infinity becomes infinity, so infinity minus limit of 1 is constant, so limit of 1 is 1 upon limit of 1 is 1, limit of 1 by n, as n tends to infinity, 1 by n tends to 0, so limit of this 1 by n is 0, 7 into 0, 0, so 1 plus 0, so infinity, in numerator there is infinity upon 1, so infinity upon 1 is infinity, so limit is infinite. The limit of Sn is not a finite number, it diverges. Okay, so we have find the limit of Sn, which is infinity. Okay, understand? Now another example, Sn is given as like this, so we will find limit of this. So limit of Sn as n tends to infinity, okay, is equal to, now we maintain this cube as outside, so this becomes limit of numerator and denominator. Before that we divide numerator and denominator by n, so okay, so this becomes limit of Sn is equal to limit of a, so divide, we have divide numerator by n, a plus b by n. Okay, since we have divided whole numerator by n, so here n get cancelled and here b by n. Also here, now in denominator we divide whole denominator by n, so this n get cancelled, so c plus and here d by n. So this is equal to limit, again limit of xn upon yn is equal to limit of xn upon limit of yn. So limit n tends to infinity of numerator a plus, okay, and here is cube. Okay, so we can write this as now limit of a plus b by n upon limit n tends to infinity of c plus d by n and cube of this thing. We can take limit inside. Okay, this becomes limit of n tends to infinity a plus, just now separate the limits, limit of xn plus yn, so limit of xn plus limit of yn plus limit n tends to infinity b by n upon limit n tends to infinity, separate limit in this bracket also, so limit of n tends to infinity into some constant c plus limit of d by n, so limit n tends to infinity into d by n. Now limit of some constant number a is a, so a, and as n tends to infinity 1 by n tends to 0, so limit of b by n is also 0, so a plus 0. Now so cube of this, okay, so a plus 0 upon limit of c, constant c, limit of b by n as n tends to infinity is 1 upon n, tends to 0. So limit of d by n is also 0 cube. This becomes a by c whole cube. See, as n tends to infinity, denominator is tending to infinity. So b upon infinity tends to 0. Similarly, on other way, we can take d outside. Limit of 1 by n as n tends to infinity is 0. So d into 0, 0. So this becomes 0 and cube of whole bracket. So limit of this is a by c whole cube. Okay. Now we will see two more examples. Okay. Now these two examples have been previously asked in university examination. Okay. So we have to find limit of this n term. So first, here 10 raised to power n, here is 10 raised to power n. So we will try to divide numerator and denominator by 10 raised to power n. So limit of Sn is equal to limit of, divide this numerator and denominator by 10 raised to power n. This becomes, so here there is no 10 raised to power n, so this term becomes 2 upon 10 raised to power n, plus here if we divide by 10 raised to power n, this 10 raised to power n get cancelled, so there remain only a number 3. Here also divide this whole term by 10 raised to power n, so 3 upon 10 raised to power 10 raised to power n plus this is upon 10 raised to power n. Here 10 raised to power n get cancelled, so here we get 3 upon 10 raised to power n plus in this term 10 raised to power n get cancelled. Okay, so plus here remain only 4. Limit n tends to infinity. Okay. Now we will separate limit. So limit xn upon yn. So limit of xn upon limit of yn, and again there is separation in this plus. So limit of this plus limit of this, limit of this plus limit of this. This becomes limit n tends to infinity 2 upon 10 raised to power n plus limit of this constant 3, which is 3, upon limit n tends to infinity 3 upon 10 raised to power n plus limit of this constant number 4. Okay. Now as n tends to infinity, 10 raised to power n tends to also infinity. So 2 upon infinity tends to 0. So limit of this 2 upon 10 raised to power n is equal to 0. Limit of this constant 3 is 3. Again as n tends to infinity, this 10 raised to power n tends to infinity. So 3 upon infinity tends to 0. Something upon infinity tends to 0. So limit of this is 0. Okay. This is 3 upon 10 raised to power n. As n tends to infinity, the matter going to infinity. So 3 upon infinity tends to 0. As denominator goes on infinity, value goes to 0. So 0 plus limit of this constant 4 is 4. So limit is 3 by 4. So limit of this Sn is 3 by 4. Okay. Now this one more important example. Here 4 raised to power n plus 2 plus 3 raised to power n plus 1 and 3 raised to power n plus 2, 4 raised to power n plus 1. So first we will try to take some common part in numerator and denominator. Okay. So we will try to take common 4 raised to power something. Okay. Here is 4 raised to power n plus 2, here 4 raised to power n plus 1. So we will take 4 raised to power n plus 1 common. So limit of Sn is equal to limit of, now take 4 raised to power n common. Okay, so 4 raised to power n, so 4 raised to power n plus 1 we can take common. So we have taken 4 raised to power n plus 1 common from numerator. So here 4 raised to power n plus 2, so here remain only 1, 4. Okay, plus here there is no 4 raised to power n plus 1. So after taking this common, to maintain this value, we have to divide this by 4 raised to power n plus 1. So 3 raised to power n plus 1 upon 4 raised to power n plus 1. So 3 by 4 raised to power n plus 1. Okay. Upon, now again we will take 4 raised to power n plus 1 common from this denominator. So 4 raised to power n plus 1. Okay. Now here 3 raised to power n plus 2. So we will write this as 3. Okay, so we will use the other brackets to avoid confusion. Okay, now what we have done, we have just take 4 raised to 1 outside, 4 raised to 1 n plus 1 outside from numerator. So 4 raised to 1 n plus 1 into 4, we get 4 raised to 1 n plus 2. So 4 raised to 1 n plus 1. So 3 raised to 1 n plus 1, a plus 3 raised to 1 n plus 1 as it is upon 4 raised to 1 n plus 1. Is 4 raised to 1 n plus 1, 4 raised to n plus 1 get cancelled. So remain only 3 raised to 1 n plus 1. Okay, so this is okay. Now we are again trying to take outside or take common 4 raised to 1 n plus 1 from denominator. But here 3 raised to 1 n plus 2, we can write this as 3 raised to 1 n plus 1 into 3. Okay, so we can write this as 3 into 3 by 4 raised to power n plus 1. Why we are written like this? Because 3 raised to power n plus 1 into 3 becomes 3 raised to power n plus 2, and we have taken 4 raised to power n plus 1 common, and here there is no 4 raised to power 1 plus n. Okay, so we have divided by 4 raised to power n plus 1, so as it gets cancelled. Okay, so remains only 3 raised to power n plus 2. 3 into 3 raised to power n plus 1, 3 raised to power n plus 2, 4 raised to power n plus 1, and 4 raised to n plus 1 get cancelled, so 3 raised to power n plus 2 only. Plus we have taken 4 raised to n plus 1 common, here 4 raised to n plus 1, so plus 1. Okay, bracket complete. Now take limit as n tends to infinity, but this value get cancelled. So take limit of this part, so this becomes, this is equal to limit n tends to infinity of numerator and denominator. So limit n tends to infinity of 4 plus limit n tends to infinity of 3 by 4 raised to power n plus 1 upon limit 3 into limit n tends to infinity of 3 by 4 raised to power n plus 1 plus limit of this constant 1. Okay, now see here, limit of 4 is 4, limit of 1 is 1. But what about limit of 3 by 4 raised to power n plus 1? We have seen in this lecture that limit of x raised to power n is equal to 0 when value of x is lies between minus n plus 1. Okay, whenever mod of x is less than 1, limit of x raised to power n plus 1, n plus 2 is equal to 0. See, 3 by 4 is less than 1, and mod of 3 by 4 lies between, so 3 by 4 lies between minus 1 and plus 1, so mod of 3 by 4 is less than 1, and limit of this 3 by 4 raised to power n plus 1 must be equal to 0. So we are using that theorem here. Okay, so limit of this is 0. This is the reason we have taken 4 raised to power n plus 1 outside and not 3 raised to power n plus 1 outside. If we take 3 raised to power n plus 1, here there will be 4 by 3 which is greater than 1, and there were some problem in finding the limits. Okay, so our aim was to take the value here such that which is less than 1, and we have a formula, a limit of x raised to power n is equal to 0 whenever mod of x less than 1. So here mod of 3 by 4 is less than 1, this number is less than 1, so its limit as n into infinity 3 by 4 raised to power n plus 1. Limit of this term is 0. Similarly, limit of this term also 0. So this becomes, so limit of 4 is 4, limit of this is 0, limit of this 0, 0 into 3 0, plus limit of this 1 is equal to 4 by 1. So it is 4. Okay, so limit of this is 4. Okay, thank you.